Hello everyone, welcome to the episode 31 in hexadecimal of Debugging TV Frames program. You can type your questions during this episode. If I can't answer particular questions now, I then post answers on the website debugging.tv. This episode is about heap leaks and their classification into explicit and implicit leaks. And we also do corresponding parameter reconstruction for case study when I do memory dump analysis. So I recently, while preparing some case studies, modeling applications for one of forthcoming trainings, I found the need to split leaks into two categories. The first one is explicit, when we have allocation requests but forget to deallocate or free memory. And another category is implicit leaks. For example, when we call some API functions, for example Win32 or any other, but they internally allocate memory, but we forget to call missing API functions, forget to call functions that, for example, destroy this internally allocated memory. And also another case when we have API calls with some wrong parameters, maybe due to corruption, and because this internal API allocates memory, then with this wrong parameter there could be much more memory allocated. So let's look at some case study. So here's source code. So we try to output some string, some text in a window, but the size of this string becomes corrupt. So here I model this corruption by explicitly setting the size to some huge value. So initially I tried to model this situation when we don't have enough memory, so to get some not enough memory error, but with some values I found that what happens is that application immediately grows in size to several gigabytes, like with this value on my machine, modeling machine, and then it crashes. And this slows down the system significantly, especially when crash dump is saved. So what we do, I already got a crash dump for this situation, so I do some analysis. So what I do now, I open WinDBG and open a crash dump. So you see this crash dump, actually application is very small, very small, but the crash dump is 2 gigabytes. So I open it and I open a log file because I'm going to post it later. So let's create a log file. name it simply. So what we do first, I fix symbols. Enjoy a lot. So because of this huge size, 2 gigabytes, let's check heap statistics. Maybe that was a heap leak. So what we see, there are no large reserved blocks. Everything seems to be normal on first sight. So maybe there was large virtual memory allocation. So let's check addresses. Let's check virtual memory regions. The address command. So what we see here is that heap actually gets 2 gigabytes of memory. Also here's usage summary here, you see. And it's all busy. So let's come back to heap region, to heap statistics. And we see this virtual block. Maybe there was large heap allocation. Large allocations are not going to heap segments. They are allocated as virtual blocks. So let's inspect this one. So we see one is indeed there is, but its size is huge. So let's copy this and see what it is in decimal. So you see it is more than 2 gigabyte. And what we can do, we take this base address and let's dump the first bytes of it. You see there is something like, if you can read, hello. It's not really Unicode because you see that hello world, you see that each character occupies 4 bytes. So let's go to source code. Remember, we try to output hello weird, not hello world, hello weird. And you see that here, hello weird, and you see that occupies 4 bytes. But let's check stack trace because there was a crash. And let's repeat another key to remove warnings. So what we see, exception processing code. But the crash happened in this function, double wide character mapping string. So maybe Unicode character was indeed doubled. And so this is why we have, for each character, we have 4 bytes instead of usual 2 Unicode bytes. So what else can we do with this crash dump? Let's do some parameter reconstruction. So let's check the return address. So you see the text out was called. Let's take this return address. So imagine we don't have source code to look at, and we want to reconstruct parameters passed to text out. You see we also don't have symbols for application called last call. So we disassemble backwards our return address. So we see some function was called indeed. Let's double check because this is indirect call. So let's dump the value with symbols. we just need one value. We see that indeed text out Unicode version was called. Also, we need to check parameters for text out. Let's go back to source code. We see the text out as 5 parameters. The first 4 are passed through registers ICX, RDX, R8 and R9 on 64-bit platform, but the parameter we are interested in is the 5th parameter, and it is passed through stack. So let's go back to our disassembly. And here what we see that through ICX the first parameter, RDX the second, R8 third parameter, R9 fourth parameter, and 5th parameters they usually pass through stack, and usually this is ISP plus 20. And so we need to know the value of this stack pointer at the time we call this function. So if we know the value of stack pointer, we can look at stack region and find out the values. So to know the stack pointer, we can look at stack region and find out when return address, where return address is saved. And return address is saved when we call text out, and this is this value. So what we do, we find out the value of stack address and that pointing to this saved return address. So what we do, we dump with symbols. So we use this child column, child SP column. So we dump. So what we do, we dump this value from text out to the next one. So we dump this stack fragment. Here we see the saved return address. So remember we used to disassemble it. So basically what happens when this return address is saved is that the value of stack pointer is decremented by 8. So this is now our value. So it is decremented by 8. So let's copy it. And but we are interested, say for example, let's double check the 4th parameter. This is the value of stack pointer plus 38. So we add 38, but remember that stack pointer was decremented by 8, so we need to add another 8. So and now if we do DPS, we get, actually not DPS but DP, let's say let's double check again. Oh, actually it's 40. This is our 4th, not 38. 38 is the first parameter. So let's add 40. So we get this. So this way, this stack pointer stack address points to this value, and this should be the address of that string we try to output. So because this is Unicode string, we use du, so we see indeed hello world. But our fifth address is passed through stack. So if we do the same but add only 20, we get this size that was passed to text out function. And if we go to source code, we see indeed that this value was passed. So in this case, using source code is very beneficial to double check this strategy. So what we were able to do, we were able to reconstruct parameters passed to text out and see why we got this implicit leak. So this is all for this demonstration. And finally, this is the usual ad slide of forthcoming training sessions and free webinars. Please note that next week starts accelerated Windows malware analysis training, and in October we also plan a new training for disassembly, reconstruction and reversing. So again, thank you for watching this episode. Please later check out the slides and recorded video from debugging.tv. The next episode should be on 26th of August due to training sessions next week. Thank you. Bye-bye.